leading statistics. It's one of the two leading statistics department in Germany next to Munich. And he was trained in Munich. So he was trained in the two probably best statistic departments in Germany. And Andreas is very interested in regularized regression methods like regularized linear mixed models, regularized additive mixed models, and recently he became interested in Cox Frailty models. He did a lot in sports analytics, but is now also interested in medical applications of his topics. But his sports analytics is still very interesting because he predicted the World Cup outcome 2014, 2018. I think 2014 was pretty good, 2018 not so good. And we can ask him afterwards who will win the Champions League this year, if he made a prediction model. But now let's hear him talking about regularization effect selection in Cox Frailty models. Okay.
Thank you so much, Daniel, for first of all the invitation and for the kind introduction. Yeah, actually, I'm giving that talk from Munich because due to the coronavirus, I'm also in my home place now. But yeah, as Daniel said, since 3 years, I'm working at the Department of Statistics in Dortmund. And today I will talk about regularization and effect selection in so-called Cox Frailty models. We will see in a couple of minutes what Cox Frailty models actually are. And this is a joint work together with Trevor Hasty from Stanford University, Thomas Kneip from Göttingen, and Gerhard Tutz, who was my PhD supervisor in Munich. And this whole work on the Cox Frailty models in this group that I'm presenting today is ongoing since about 5 years. I will present you actually today 2 parts of that project. One project part is already finished, and the other part is still ongoing. And there is a lot of things still to do in the Cox Frailty model, but I will give you an overview. And I will start with a motivation. So there was a certain data set about Germany's current panel analysis of intimate relationships and family dynamics. In short, the data set is called PairFam. And this PairFam data set allowed us, after some data pre-processing, to actually obtain a data set that is structured for event data analysis, or you could also say like survival analysis. So we have an outcome, which is in this case, the response variable is, I called it child. It's actually whether a German woman became pregnant with her first child. And actually the data set that we created had more than 2,500 women, German women. And for these women, we know the precise time point, actually the precise day we know the precise day when they gave birth to the first kid, so we could count back more or less like 8 months when we think that they realized that they got pregnant with the first child. And we have a bunch of variables for these women. Like, for example, we have the current job status, we have the relationship status, we know their religion, the number of siblings they have, and a bunch more. And then we also know the federal state, the German federal state in which they were born. And the interesting part of the data set is, first of all, that some of these covariates are time varying, which in a time to event framework is always a bit annoying, because it means that whenever a covariate changes, we have to make a split in the data set. So the starting time point for this analysis, we were taking the 14th birthday of these women, because we just were thinking that kids that were, or pregnancies that were coming up before the 14th birthday are kind of very unregular. And that is why the time point 0 in that study is actually considered the 14th birthday of these women. And then we see here the ID number. So the first couple of rows in that data set correspond to the first woman. And we see that for the first year, she was still in school. Then there was another time period where we had no information about her job status. Then there was a quite long time interval. So the time is measured in days here, where the woman was unemployed or maybe just housewife. Then she got full-time employed. And finally, her relationship status was changing from single to having a partner, and right a couple of days afterwards, she actually got pregnant with the first child, which is maybe a little bit of an unusual time course for that woman, but I think you can now imagine how the data set looks like. And due to that time varying covariates, we have to do these time splits. So whenever one of these covariates is changing, we have to do a split, and those time intervals where we just had to stop because of the splitting, we consider as censored time intervals, and just in the last time interval of each woman, there might be a final event, in our case, pregnancy. And due to that structure, we started with the 2,500 observations for these women, but the new data set, because of all these time splits, now has more than 20,000 lines. So we get, in some sense, we could say we get a bit, yeah, kind of high dimensional. But we will come back to that data set later, because now I just want to just quickly show you what this talk is all about. First, I want to introduce the so-called Cox Frailty model with time varying effects. Then I will introduce a so-called penalization framework in order to obtain some kind of regularization. Then I will come back again to this pair-farm data application and show you the results when we apply this method on that data set. And if we have still some time, I will show you a quick extension on boosting. That is the second project part, which we are currently working on. So, but let's start with this Cox Frailty model. And we will first start with the very classical Cox model, which maybe some of you have already seen. So the classical Cox model is modeling the hazard rate, which here is denoted by lambda, based on some covariates, which are collected in that vector xi. So that's typically small p, a number of small p covariates. And then the covariate effects are given by that vector beta. So beta is the fixed effects vector, and that is the classical Cox model, where we have time constant linear effects beta of these covariates. And then there is lambda naught. So lambda naught is the so-called baseline hazard. The baseline hazard is typically, it's typically non-linear or non-parametrically modeled. It's not the main focus of the analysis typically. So people use something like the Nelson-Allen or the Kaplan-Meier estimator for that, which is a non-parametric estimator. But in principle, it's just a shared baseline hazard, which we would obtain if we put all the covariates to 0, or which we could say is kind of the average hazard of all the individuals in the study. And the hazard in general, the hazard lambda can be interpreted or can be defined by this rather complicated looking formula, which mathematically speaking is a conditional probability conditioned that a certain individual has survived up to small t, that the individual will experience an event in the next small time period delta t, divided by delta t, and then taking the limit delta t to 0, which means it's actually the intrinsic probability having survived up to today, receiving an event or experiencing an event right now with a normalization. So that is kind of the interpretation of this hazard rate, and the hazard rate is the crucial model part that we are modeling in such a Cox model. And inference, which means estimating those beta coefficients, that is what we are typically interested in. The beta coefficients tell us, for example, what is the effect of smoking, what is the effect of alcohol consumption in some medical example, or in our case of the pair-farm study, it could be what is the effect of being unemployed or having a very high job status on the fertility, because in our case, we wouldn't even talk about a hazard, because kind of becoming pregnant is not a bad thing. So it's actually just modeling the intensity of a transition into motherhood, kind of. And typically people use the so-called Cox partial likelihood, which is just for mathematical convenience, making the estimation a little bit simpler, but we will come back to that later. And what is also nice, and that is now the first step of regularization, Tip Shirani, another researcher from Stanford, he was inventing in 1996 the general technique of the lasso. The lasso is the least angle shrinkage and selection operator, which is a technique in regression for attacking or tackling the p larger than n case. So if we have more covariates than observations, that's typically a problem because some numerical issues occur. Design matrices don't have full rank anymore and are not invertible and things like that. So we need some sort of regularization. And Tibshirani in 1996 was inventing this lasso technique, which actually extends the likelihood by adding a penalty term. And just 1 year later, after the original lasso, he was inventing another strategy for these Cox models. And the idea is just to penalize the beta coefficients, the absolute values of those regression coefficients from up here, and introducing some penalty parameter, which I denoted here by xi. So xi is controlling the overall strength of the penalty. And if we add this penalty term to the partial likelihood, and then we maximize the partial likelihood, together with that penalty, then we get some sort of regularization and estimation becomes more stable. And you see, this technique is already more than 20 years old now, and it is very nicely implemented in software packages. For example, in R, there is the GlimNet package where you find this technique. Now we want to make one extension to that Cox Frailty model. You see that the new guy is in blue. The new guy is actually what is called a frailty, but actually it's nothing else than the random effect. So in Cox modeling, this is just a scalar, and it's just a factor that comes in front of that typical Cox model part. And the frailty component small b is actually to account for clusters in our observations, like some sort of dependencies between clusters, or you can also say the heterogeneity between clusters. So actually, that is why we also now need this double notation in the indices, because we have now we have I, which is modeling from 1 to n the number of clusters, and for each cluster I, we have then ni repeated measurements. So in our pair farm data set, we can put, for example, a random effect on the German federal state. So for example, if we take one federal state like Bavaria, then we have like a lot of women that come from Bavaria. So we have kind of a lot of repeated measurements from Bavaria. And for a different federal state, all the women that come from a different federal state, they obtain a different random intercept. But as the random intercept is not, in this way the model is written, it's not part of the predictor, it's a factor in front of the model. That is why people call it actually a frailty. And later on, when we want to do estimation in such a Cox Frailty model, then we somehow have to integrate out the random effects, and that is mathematically typically a complicated thing to do. That is why people typically assume a gamma distribution for those random effects, because when you have a gamma distribution, the integral would actually very nicely, can kind of be sorted out very nicely. And that is why people mostly use that gamma distribution for this multiplicative random intercept. And there is a lot of R packages available where different frailty models are available. So in these, there's 3 packages that I have named here. Probably the survival package is the most famous one. And there it's actually possible to specify different frailty distributions. What we were actually deciding to do is not to focus on some kind of multiplicative gamma frailty, but we were actually saying, well, we can just take the factor b and can shift it into the exponential part, okay? So when you would assume a log normal for that factor, if you instead shift it into the exponential, then you could say, okay, well, for the inner exponential part, we can assume actually a direct Gaussian, okay? So a direct Gaussian inside of the exponential would lead to the same result as a log normal if we put it as a factor in front of the term. So a log normal frailty is nothing else than a Gaussian random effect inside of the predictor. And the cool thing is that if we use this kind of model specification, we are not restricted anymore to have only random intercepts, but we could even include a whole vector, which I called now U. So U is a vector with Q variables, which is a covariate vector that is now associated not only to a random intercept, but also to some random slopes. And typically the first entry of that vector, so this one here, that would typically be just 1, because that is reflecting the random intercept, and all the other components here are really random, like covariates that are associated with a random effect, and they would actually be associated with a random slope parameter. And then for the vector bi of random effects, we would, as I said, assume a regular Gaussian with a mean vector of 0 and a Q matrix, which might depend on some unknown parameters theta, which is the random effects covariance matrix. So the model becomes more complicated. Of course, there's more parameters to estimate. We now don't only have to estimate the betas, but we also have to estimate the B, and we also have to estimate the theta. But the model is also much more flexible and can also account for these these cluster structures, in our case, on the German federal states, for example. And then there is one final, and that is actually the crucial extension that I want to do. In a time to event analysis, it's not necessarily the case that a certain covariate effect beta is time constant over the whole time interval. For that reason, I will now distinguish, and that is the new blue guy. So there is a vector z, which is a vector from 1 to small r. That is a number of covariates for which we say, well, the regression effects beta are not staying constant, but they might vary over time. So we now distinguish between time constant covariate effects and time varying covariate effects. So for example, in a medical application, we could have something like that. When you, for example, have a cancer disease, as soon as the doctor has noticed the cancer disease, there might be a strong effect of a smoker, but this smoking effect might fade out after some time, or maybe might even increase and worsen after some time. So a regression effect gamma that is changing in some way over time, that is what we are now focusing on. And for that reason, our predictor now has 3 parts: a linear time constant part, a linear time varying part, and the random effects. And the question is now, how can we estimate those flexible time varying guys? Because if we have absolutely no prior knowledge, the statistical modeler has no idea how these effects actually look like. So one very nice and flexible way to do that is to expand those potentially time varying effects gamma in some sort of spline basis. So we are actually using B splines here. And the idea is that the case potentially smooth effect is expanded in a number of capital M basis functions. In our case, as I said, B splines. And then it means that for each B spline, there is one alpha coefficient that is actually modeling the effect of those splines. And in this way, we get a very high number of parameters, because for each of those gammas, like M, the number of splines is typically something like 20 or even 30. So there is about 20 to 30 parameters involved for each spline. And that increases the number of parameters extensively in that model. But however, it also increases a lot of flexibility. So we will see later on that some very interesting effects gamma k could be potentially estimated. And so the idea of B splines is actually not very new. There is 2 researchers called Paul Eilers and Brian Marks, and they came up with the idea of B splines, or if you use penalized B splines, they are called P splines, already in 1996. And I just realized last year in 2020, they just came out with a very nice overview book. So if you're more interested in spline modeling techniques, there is a nice book. It's called The Joy of P Splines, which came out last year. And then there is Simon Wood. It's a researcher he's a researcher from the UK. He used to be in Bath, but now I think since half a year he's in Edinburgh. He's I could say his whole career was devoted to spline modeling, and he has written a very nice book that's called Generalized Additive Models in R. So he's doing a lot of research as well on those spline models. And so, yeah, we were actually able to just simply include them in our framework. So to sum up, we have now a rather complicated model with a still unspecified baseline hazard. Then we have the fixed effects, the time varying effects, and the random effects. And one problem is this guy. So what shall we do with that guy? And the simple answer is, if we have done all the effort to include time varying effects here, then it's not a big step anymore to also estimate the baseline hazard as a very flexible spline. And so the only trick that we have to do is to define gamma naught to be log of lambda naught. And this way I have just shifted the baseline hazard lambda naught into the exponential and call it gamma naught. And so you see that in comparison to the previous slide where the sum was starting in 1, the sum is starting now in 0. And we just define that the first entry of this covariate vector is simply 1, kind of an intercept. So the B-spline expansion that belongs to the first entry of that Z vector, that is actually our baseline hazard now, just a logarithmized version. And the cool thing is now that we have put all our model components now into a certain predictor, which statisticians typically call eta. So eta ij of t is a complicated predictor with a lot of different terms, and that is varying over time. Why is it varying over time? Because those spline parts here are varying over time. And so the question is, of course, now, how can we estimate all of these parameters, the betas, the spline coefficients alpha, and the random effects? And the idea is that you could use Cox full log likelihood, which actually looks like that. So I don't want too much to go in detail there, but you can very easily verify that the log likelihood of such a Cox model looks like this. And here you see again the eta. So the eta is actually the complicated red term from above. But with that definition, we can write down a very compact form of the log likelihood. And based on that log likelihood, we would like to do maximum likelihood estimation in order to get our parameter estimates. Just to note this, the Dij is our so-called event indicator. So Dij is a dummy variable for the ith cluster and the jth repeated measurement in that cluster, which is 1 if we observed an event and which is 0 if we observed censoring. So 1 means in that case the woman became pregnant at the end of the interval. 0 means the woman was still not pregnant at the end of the interval if we put it to our application. Okay, so we want to estimate now this guy. We want to maximize this guy using maximum likelihood techniques. And what we typically need to do now is we are interested in the regression coefficients, but we unfortunately have involved these random effects. And what statisticians then typically do, they try to get from this joint log likelihood, they try to make the step to the so-called marginal likelihood, where they try to integrate out the random effects. So remember, the random effects were Gaussian. So if we have the log likelihood conditional on the random effects, then we can multiply this by the random effects density and then integrate out the random effects. But this is a typically very, very complex integral, which is not available in closed form. So what we can simply do, that is now a very technical detail, we can just use some Laplace approximation techniques. There is a very famous paper of Breslow and Clayton from the early 90s where they suggest how to do that technique. And with that technique, the integral here can be approximated. That is why I call now L approx, that is the approximate log likelihood, which now looks like this. We still have a sum over all of our clusters. Then we have the log likelihood contributions of the clusters. And instead of a complicated integral, the integral has vanished. And actually the random effects, they just appear in this approximated log likelihood as a quadratic penalty term. So the inverse random effects covariance matrix actually serves kind of a penalty matrix, where in a sandwich style, the random effects are multiplied with that inverse matrix. And that is now a likelihood that we can really work with, because there is no integrals involved anymore. And that is a likelihood that a statistician could, with regular techniques, try to maximize. But before we do that, before we simply calculate the maximum likelihood estimator of all our unknown parameters, there's typically in such a complicated Cox model, there is two major questions of model selection. The first one is, which covariates shall we include at all? So for example, does the job status of these women really play a role on their fertility? Or is there like the number of siblings they have? Does this matter at all? Well, it might be the case, but we don't know in advance of the analysis. And if we decide that a covariate shall be included in the model, then a second question would be, does the covariate have a time constant or a time varying effect? Which means if I go back, shall I put the covariate here or there, like in the time constant or in the time varying part? And that is very complicated questions that you typically simply don't know. So what you would like to have is a statistical model which can do this automatically for you, and you don't have to decide, the model will do it for you. And the two strategies that I want to propose here is penalization and boosting. And we start with the penalization. The penalization is, well, this of course looks horribly complicated. That is a certain penalty term that we will actually add, or to be more correct, subtract from that likelihood. So remember, that was the intermediate result. That was the approximate log likelihood, which we could simply maximize. Then we would get our parameter estimates. But now we want to address these questions of model selection. So what we do is we subtract this horribly complicated looking penalty from our log likelihood, and then we try to maximize the penalized log likelihood. But actually, the penalty is not as complicated as it looks like. So we have the psi here. The psi is the overall amount, the overall strength of that penalty. Then we have a second tuning parameter, which is zeta. So you see, zeta is a proportion. Zeta is actually deciding how much weight we put on this part of the penalty, and 1 minus zeta, which is the rest, how much weight do we put on that penalty. Let me start with the second one first. So here you see the main thing is the L2 norm of the alpha coefficients of those spline coefficients. That actually means if we put a lot of penalty, a lot of strength on that part, then all the spline coefficients would be shrunk down to 0, which actually would mean that the whole spline would be estimated to 0, and that would actually mean that the covariate gets kicked out completely from the model. And in the first part, we have something very similar. We also have an L2 norm of a certain vector, but now this vector is not the alpha coefficients themselves, but it's pairwise differences of neighboring spline coefficients. So if we put a lot of penalty strength on that part, then actually neighboring spline coefficients would be estimated equal. And that would mean that our spline does not become a very wiggly thing, but our spline would become a horizontal line, which actually means a time constant effect. So the combination of these two penalties can kind of solve the issue of the second part, which controls whether a covariate should be completely kicked out of the model, and the first part, which decides whether the covariate should get a time constant or a complicated time varying effect. And the blue and the red parts are just some weights. So the problem is that this vector, the vector in the L2 norm here, is by one coordinate shorter than this one. So we have to account for the different sizes of these groups. And the blue one, that is just a small fanciness that we can add here. We can use so-called adaptive weights where we plug in the inverse of the unregularized maximum likelihood estimator. There is some literature that this just yields more stable estimates, and that's just making the whole thing a little bit smoother, so to say. But we don't have to worry too much about that. And so the crucial thing is actually, as I said, so psi and zeta, they are very relevant because they are the tuning parameters that control what is the overall strength of the penalty and what is the separation between forcing the splines to become 0 and forcing the splines to become time constant. And so these guys need to be chosen very carefully by an appropriate technique. One technique that statisticians typically use is k-fold cross-validation. The only problem with that is that it becomes very time consuming. And then there is one last thing, but that's really just a very minor issue. we still want to have the baseline hazard, which we have also expanded in splines. For the baseline hazard, we just give it an extra penalty. So that is the baseline hazard penalty, which is just taking care that the spline coefficients of the baseline hazard become not too wiggly, not too different from each other, so that this just guarantees some sort of smoothness of the baseline hazard. So to sum up, we would now take the approximated likelihood, which we received from that Laplace approximation following the Breslow and Clayton approach from the early 90s, and then we are subtracting the penalty for the baseline hazard and the very complicated penalty from the previous slide. And then there is only one other problem, namely that these penalties that we see here, these L2 norms, they are actually not differentiable in zero. So if we would plug in the zero vector in there, then we cannot calculate the gradient, which is the vector of first derivatives, which we would need for numerical optimization. So for that reason, we follow an idea of a paper of 2017 of Margret Oelker and Gerhard Tutz, where they propose to use local quadratic approximations of these penalties. That's a very technical detail, but I will nevertheless quickly show you the idea. So for example, if you have simply the absolute value function you see here in gray, it is obviously not differentiable and has a very sharp edge down here in zero. So in that point, the absolute value function is simply not differentiable. But if you quadratically approximate that function by a square root of the squared variable plus a very small value, then we get the black curve, which looks actually equally, except for in that problematic area, it looks slightly different. And a similar idea we can do for these guys and these guys. So all of these L2 norms, which are not differentiable in zero, they can be local quadratically approximated, then they become differentiable, and then we can actually switch to a very conventional Newton-Raphson algorithm, which is a typical estimation technique in statistics. When it comes to calculating the maximum likelihood estimator, you need the gradient, the vector of first derivatives, and you need the Hessian, the matrix of pairwise second derivatives. And now, based on these local approximations, this is possible. And then you can use a simple Newton-Raphson algorithm, which in our case would look like this. We need some starting values, and then we would say we use a two-stage switching algorithm. So the new fit will be based on the old fit plus a certain update, and the update is given by the score vector, which is the vector, the gradient, actually the vector of first derivatives, times the inverse of the Hessian, so to say, right? So probably that is much too technical for you guys, but don't worry about it. That is actually the form of a standard Newton-Raphson algorithm. We update our estimates by some kind of mechanism which is based on the first and second derivatives. There's a very standard way of some kind of gradient-based optimization routines. And then in a second step, we still have to maximize the estimates of our random effects covariance. So if we have chosen a certain fixed value for our penalty strength parameters, then we would just switch between these two steps, A and B, all the time until convergence. And if the algorithm has converged, the resulting parameters are our regularized Cox Frailty model estimates, right? So looks very complicated and is of course a very technical thing to do, but I will show you now on the application of the pair farm data that if you put all these technical algorithmic details aside, the results of that approach are rather nicely interpretable. So just to bring back to your mind the data set. So this was the original data set where we had these 2,500 women. We have all these time so these splitted intervals. We have our time to event response variable, which is 0 for censoring and 1 for women that became pregnant at the end of the interval. And that is also with the pregnancy, our observation period is directly done for that woman, okay? And then we see it goes on with the next woman. And we have a lot of covariates, and I show you them in more detail. So actually we have 3 covariates which were not changing over time. So the religion, we had a fixed value for each woman about her religion. And you see here the proportions in the data set. We had women with no siblings, 1, 2 siblings, and then there was a 4th category, which was 3 or more siblings. And we also have the educational level of the parents, which we were given as a time constant variable. And then we had 3 other variables which were actually changing over time. So because these women, typically they were first in school, then they were, for example, part-time employed, or then they were full-time employed, then they were maybe job seeking and so on. So you see, this is something that can change over time. And the same, of course, for the relationship status. Sometimes these women are single, then they get a partner, then maybe they move together with a partner, and then they even become married, but maybe they get divorced and then they are single again, and so on. So these covariates can change all the time. And whenever a covariate changes, we have to do a split in our time interval, right? So that was the way the data set was designed. And in order to account for these regional fertility differences, we also included a random intercept for the German federal state, which could be, just making a stupid example, it could be the case that in Bavaria, the women get much more babies than in Lower Saxony or in North Rhine-Westphalia. And if that would be the case, then there could be a positive random intercept for Bavaria and maybe a negative random intercept for North Rhine-Westphalia. And for that, we incorporate these random intercepts. Okay, so now we would like to run this algorithm, which I introduced, which looked very technical on the previous slides, which I called Cox Frail, which is a penalized Cox Frailty model. And as we have seen, due to these time splits, our data set became quite large. And so it's actually not so nice to run this k-fold cross-validation on our tuning parameters. Remember, we had these 2 tuning parameters, psi and zeta, and so we would actually need a 2-dimensional k-fold cross-validation, which is very time-consuming and yeah, takes horribly long, unfortunately, because it's a very complex estimation mechanism. So the good thing was that Trevor Hastie had a very ad hoc idea what we could do. So we actually said, okay, the second penalty parameter, which is just controlling the separation between forcing splines to 0 and forcing splines to become time constant. Well, that guy was simply put to 50% on both, which is of course very rude, but we were lazy and we're just doing this. We were just wanting to see what happens if we throw that model on our PairFam data. And for the second tuning parameter, which is maybe so to say the more important one because it controls the overall strength of that idea, was actually to additionally to the covariates that we have seen, like job status and family status and so on, we just simulated 10 noise variables for which we know that they have absolutely no effect on the response at all. So we just simulated 10 additional noise variables. Then we started to fit the model with a very large penalty amount. And then we successively decreased the penalty strength and we stop right before the first of these weird noise variables is selected by the procedure, because we know that is actually not a good thing to do, right? It's not reasonable to include noise variables because we know that they are noise. And just to show you quickly how you can run that algorithm in R, so you have to specify a formula in the typical survival context. So you specify a time to event response. Then you can specify a second formula where you can put all the variables for which you believe there might be time varying effects. So in this application, we actually put all of the covariates there because we were not sure about all of them. And then you put a third formula where you specify the random effect structure. So here, this means just a simple random intercept on the federal state. Then you specify the data, you specify the psi parameter, which is the main tuning parameter, and the zeta parameter, which is the second tuning parameter, can actually be specified in the control argument. And what people typically look like first when they have run some regularization or some penalization model, they typically investigate the so-called coefficient buildups. So what you see here in that weird graph, which looks horribly confusing at the first glance, you see the L2 norm of the spline coefficients for each of those variables. And on the x-axis, which is log of xi, you see the logarithmized scale of the strength of the penalty. So on the very right side, we have a very strong penalty, and you see all of the coefficient paths are still down to 0 because the penalty on the L2 norms is so strong that they are all estimated down to 0. But if we successively decrease the strength of the penalty, then we see that the red curves, which in this case are the coefficients of the spline coefficients of the relationship statuses, well, they are starting to increase, and also the blue covariate, which is the educational level of the women, also starts to increase. And then if we further decrease the penalty, more and more of these coefficient paths start to increase, and then there is the black dashed lines. There is 10 black dashed lines. That is the L2 norm of the spline coefficients of these noise variables, which we additionally simulated into the data set. And so we see at a certain time point or at a certain penalty amount, one of those dashed lines really starts to come up as well. And that is where we very abruptly stop the procedure, because we don't want this. We don't want to have any of those variables in the model for which we know that is noise, because that is complete nonsense to include such variables into the model. And that was the ad hoc strategy that Trevor Hasty suggested in order to find the optimal amount of penalization on our spline coefficients, which is very nice because it avoided a lot of time-consuming cross-validation work. But what is now much more interesting is if we now have the optimal penalty strength, which is this line, this amount of penalization, we now want to see, because this what we see here is just the L2 norm of the spline coefficients. What we want to see is the splines themselves. So what you see here is, for example, the final estimate at this optimal amount of tuning in comparison to the reference level single. We see here over time. So you see time is here now given in years. So we start with the 14th birthday of these women up to around 40. That was the oldest woman in the data set, was around 40. And what we see here is as a black line, we see the spline that was estimated by our model. And the first thing that is obviously the case, the model was estimating a positive beta coefficient, potentially changing over time. So actually this should be denoted by gamma, because we called the time varying coefficients by gamma actually. So the black line could be a time varying gamma, but it looks perfectly time constant. That is due to our regularization. So the model has decided that there is no time variation going on for the level partner, but there is a general very positive effect on the fertility of these women compared to the reference level single of having a partner, which is of course perfectly reasonable, because you probably should have a partner in order to become pregnant, at least in most of the cases. And in order to get some idea of the uncertainty that is involved in that, we compare this to a conventional Cox model. So the conventional Cox model is the red line. And the nice thing is that for the conventional Cox model, you get 95% confidence intervals directly available. So you see these dashed confidence bands. And so this gives us at least some idea of uncertainty also for our black line. So here we see that the black line is perfectly inside of this confidence band of the conventional Cox model. So you could say it does not look like significantly different from being time constant. If we take women that are in the category living together with their partner, we see there is an even more increased positive effect on the fertility, which of course also makes some sense, because couples that live together have maybe a stronger relationship than couples that are just together. And here we see that there is a slight time variation going on in our effect. But if we compare it with the red dashed confidence boundaries, then we see that this also does not really look significant. And the most interesting effect for that covariate is the category married. So for women that are married, we see there is, in particular, when the women are very young, then there is a very positive effect on transition into motherhood. but this effect is kind of fading out over time. And it is also quite clearly getting outside of the confidence bands of the conventional Cox model, which somehow could be seen as an argument that there is really something going on. And it probably could mean that couples, well, at a certain age, either they want to have kids or not, and then the status of marriage is not so important anymore as it might be the case when the women are younger. But that's, of course, the interpretation is always a little bit hard to take, but that could be some way of interpreting it. Just to give you a second example, here you see the estimated splines for another covariate, which is now the education level. So again, in black are the estimates of our model, and in red with the dashed lines, you see that the conventional Cox model. And here we see, compared to women with a medium education level, in particular when women are young and have a low education level, that is a very high effect, positive effect on transition into motherhood. But this effect seems to fade out compared to women with medium level, while for a women with a high educational level, it's completely vice versa. So women that are young and are, for example, still in school or jumping in the next stage of the career into the university or so, that is a negative effect compared to medium education. But at some point in time, or at some point of age, I would better have to say, this changes. And then we see that actually for older women, it is getting even a positive effect for transition into motherhood. Because if women completely finish the career, the academic career maybe, then, well, maybe after some age, they now feel really ready to start some kind of family life. So maybe. And then for the last category, which was women, where we had no information about the reference level, there seemed not to be much going on. And if you look at the confidence bands of the conventional Cox model, it's not really significant different from zero. So that category seemed to have no effect at all. And so the last thing that we could look on in that model fit is the baseline hazard. So the red dashed line is the baseline hazard, again, of the conventional Cox model. And we see that the conventional Cox model, which in all the other covariate effects has constant, there's no other way, it has to be time constant effects. That is why the baseline hazard, which is the only potentially time varying part of a simple Cox model, is much more pronounced than ours. So our baseline hazard would just recognize that there is an overall average increased fertility in Germany for women in the late 20s. So that is just that on average, women in the late 20s are having a little bit more, are a little bit more likely to have a transition into motherhood than for very young women or rather old women. But if you look on the Y scaling, then that is actually not so much of a difference anyway, because that is, both of them are actually pretty small effects. So most of the explanation is coming from these covariate effects. And finally, well, there is some heterogeneity on the German federal states, because we were also having these random intercepts along, and we see that there is a moderate estimated empirical standard deviation of the random effect. So I would say there is a moderate heterogeneity in between the German federal states. There is actually almost, except for some later decimals, almost exactly the same random effect was estimated with the simple Cox model. So here it seems to agree. So I think because of time reasons, I would just actually skip the boosting part, because this is even more technical. Just in very quick words, we found a nice way of splitting the splines into two parts, and then we can use an algorithm which is cycling to these two ways of either just doing a constant update of the spline or doing an update on the smooth part, which is very similar to the two penalty parts that we have seen in the beginning of the talk. And the boosting can actually, in each update step, just decide whether to update this guy or to update that guy. And I just can show you quickly how such a boosting algorithm looks like. So it actually looks a bit complicated. We have to update, we have to calculate for each single variable the best constant update and the best smooth update. And then we have to decide which one is the overall best update, and then we do a single weak update for that part, and then we run the algorithm again until convergence. And the actual thing is that we just believe, and that is what we have already observed so far, that the boosting looks even more promising than the penalization, but we have seen in the application that the penalization already also did quite a good job. So to quickly conclude, in principle, we are working on two different regularization approaches for these Cox Frailty models with time varying coefficients and log normal frailties. I introduced the penalization today. On the boosting, we are just working. The method in the end yields flexible but also sparse models. Sparsity actually means in a sense that at the optimal point where we stopped, you see that there is much of the stuff is going on later. So if we do this, if we stop here, then we get some kind of regularization. So for example, we could observe this effect was just time constant and not very wiggly time varying, right? So there is some, we can observe some kind of sparsity or simplicity in these models, but still having them very flexible. For time reasons, I completely skipped that we have, of course, investigated all of that in simulations as well. So I just showed you that we obtained some interpretable and reasonable estimates on the PairFum application. And as I quickly said in the end, the boosting approach at the moment even looks more promising, and in particular, it will be much faster. So our hope is that we can come up with this package. There will be another R package for that soon. And the cool thing is the boosting steps, they can be done in parallel. So we can use techniques of parallel computing. So if you have several kernels on a machine, you can use all the kernels in parallel, and you can allow the algorithm to do all the updates in parallel, which can be which can save a lot of time actually. And what we are currently struggling with is to determine the so-called effective degrees of freedom of a single boosting update, because if we have solved that problem, then we can actually find a very nice way of calculating the optimal boosting model, and that is what we are currently working on. So yeah, just some quick mentioning of the references. So for the penalty approach, which I presented today in detail, there is a paper in Biometrics from like 3 years ago. There is also the R package available, which I very quickly introduced when I showed you the call in R. For the second part, the boosting, there is already a conference proceeding paper available where I quickly sketched the basic idea, actually exactly that part which I was now skipping because of time reasons. Yeah, and as I told you, I hope to come out with the first version of that package very soon. The first package is already available on CRAN, which is the server of R, where we host all the packages. Yeah, and that is some additional references. And now I'm really interested about if I confused you completely or if you have some really nice questions. Thanks very much for your attention.
Okay, great. Thanks a lot, Andreas, for this really interesting and exciting talk. I think you made a very complicated method sound very easy to do. I think you explained it very well with your moving your guys inside and outside. I think it was very well done. So are there any questions for Andreas? I think we should have a few minutes to ask questions. Or, let's see, you can either ask them in the chat, or you just unmute yourself and show your video and ask a question directly to Andreas.
Sure.
Anybody with a question?
So yeah, maybe just a last quick comment from my side. So this idea of the penalty that can automatically decide for you whether you put a time constant or a time varying effect. This is very relevant for time to event analysis, because there it's always the question whether an effect is time constant or time changing. But in principle, you can use the same idea actually in any kind of a regression model. So to say, if you have a logit model, if you have a simple binary response, a person is surviving a cancer disease, yes or no, there might also be some questions like, do we have a kind of interaction effects between the covariates, yes or no? And so in principle, you can use the same penalty idea for also letting the model decide these things for you. I just put the focus today for that on that time to event analysis, but the basic idea can easily be transferred to almost any kind of regression model, so to say.
Really good, and I think that's very relevant for many of our studies. Well, you said with the random slope, but you didn't include a random slope. Is it still possible to estimate random slopes?
Yes, it is. So for example, like here, what we did here, that was again this R call. That was the call of the package in R. And so here we just put the intercept on the federal state. But for example, you might believe maybe that the relationship status has an influence that is changing over the federal state. So just to make a, the very Catholic part in Germany and Bavaria. So maybe you could say that being married in Bavaria has a very strong effect on increasing the fertility, because in Bavaria, people are still kind of old-fashioned and they don't get the babies before they are married, while maybe in North Rhine-Westphalia, this effect would not be that strong, right? And if you would like to have this, and then you could add here just with a plus, you would say 1 plus relationship status, and then you would get a random slope for the relationship status, such that the relationship status, which here has the main effect, could potentially vary for the federal states. But the penalty stuff that is going on those effects is not going on the random effect. So the random effect, that is just what the modeler is deciding. Do I want to include it, yes or no? And so the magic is going on there, kind of. Yes. And just maybe okay, there is a question now. Just wondering if this regularization will be able to cope with genetic data sets. Yeah. So when you have so many thousand genes, then probably what I would suggest to do is, I quickly go to the very beginning of the talk, when I was saying that for the classical P larger than N case, the standard lasso is available. So the package that I mentioned, which is the GLIMnet, so GLMnet, this package is available in R, but the authors are actually doing all the calculations in Fortran. So this software package is super fast. So let's say you have 2,000 individuals, but you have 20,000 genes, then it will still be ready calculated in a couple of seconds. As I am not such a good programmer, I just implemented everything in R itself. And so only for the inversions of these huge matrices, I was building a bridge to C++, because there it's a bit quicker, but still that's not helping so much. So for these very high dimensional data sets, I would first suggest to go for linear effects only and running the lasso, and then you get already a pre-selection of, let's say, the 30, 40 most relevant genes. And then maybe you could say, take these ones and then switch to this package here and see on a smaller scale whether there might be even some non-linear effect. So here you might be better with some kind of two-stage analysis. First, run a simple lasso with linear effects only, and then go on with a second step analysis, and then maybe run on a few predictors this more complicated model. But that's a very good question, because there is some kind of limit in the number of P's for my method, which you will directly feel when you run it, because it will become horribly slow at some point.
Yeah. Thanks for this question and the answer. I think it was probably a question which was many people were interested in it.
Sure. So actually, so for me, I'm a regularizer, which Danielle already said at the beginning. So we are always interested, of course, in implementing or creating new methods for these specific cases that might become necessary at some point. And so it's always, I think, good to start with a standard model and see some results there, and then think about whether to go on. So in your example, it looks like you have age as the time scale. Does it mean that the package can do left truncation? Well, yeah, it's not actually doing left truncation, it's doing right censoring. However, we were just, we were doing some kind of, in the pre-processing of the data, we were doing that left truncation. We were excluding actually all women that had already a pregnancy event before the 14th birthday, because then we were just saying, well, that is maybe very unusual, and maybe there the covariates are not that like regularly working as they are for the main group of women. So we were kind of in the pre-processing doing the left censoring, taking only those women into the sample which have survived in the sense without event up to the 14th birthday, and then we were regarding them from then on. So 14th birthday was our time point 0 then, but you are right, it's kind of a implicit left truncation. Because it seems that with time varying covariates, 2000 became 20,000 with entries at different age. Well, let me quickly maybe go back to those results. Maybe then I can answer the question a little bit easier. So you see here for those ticks, that is actually all the events that we were observing. So actually from the 2,500 women, we had 1,500 women that had an event, which is actually in a time to event analysis kind of a comfortable situation, because often the events are rare. But well, in Germany, we still have the situation that most of the families at some point get a baby, right? So that is why the majority of women at some point experience the event. And here you see there's only very few events in the data set for very young women, and there's also fewer events for very old women. And that is why that was the full range of the data set that we had pre-processed. And this data set in the end is based on the 20,000 lines, as I have showed you, well, at the beginning and also there, there, you see it like, because we get several rows per woman. And several of that rows are treated as censored, which means from the 2,500, so 1,500 women observed the event, which means about 2/3 of the women that we had. But in the extended data set, we still only have 1,500 events. So in the extended, which is kind of a blown up data set, because of the time splits that we have to do, there it's still kind of the minority that has the events. But that is an indirect thing that you can't avoid, so to say. But thanks for asking, because these are these tiny little details that sometimes not become directly clear, of course.
Well, many women have got more than one child. Can you expand it to recurrent events, this model? Because that would be interesting in psychiatry, like recurrent depression.
Absolutely. So in principle, you can do it. I mean, there's even the competing risk case that we don't have like women only to become pregnant. So women could have kind of a, so for example, I mean, for example, if a woman dies in the study here, let's say from a car accident or something like that, that would in our case be also just a censoring, right? Because she would be censored and we don't know what would have happened later on. But if you think about medical examples, we could say, one is either death or maybe rehospitalization, and they could even be competing risk. So it would actually just mean that all the mathematical part becomes a little bit more complicated, because then we have two different types of likelihoods, one for, or like we would already from the very beginning start with two different hazard rates. One hazard for rehospitalization, another hazard rate for death. But in principle, you can do the same mathematics for this competing risk setting. It does not make things easier, but it's possible. It's principally possible. Yeah.
Was there any other question for Andreas? Yeah, I think I also thought this was the comment.
Yeah. I was also, I was already since 10 years working as a statistician. And I have never before thought of this and heard about this. And I was actually also super surprised and happy when Trevor came up with this idea, because it feels so natural, right? You have a data set with like 5 or 10 covariates, and then you just randomly add variables for which you know that they are nonsense. And then you just see at what point do they jump in. And then it's kind of a natural point where you say, no, that shouldn't happen. There I should stop. And this is well, but you know, Trevor is like just one of the most famous statisticians at the moment. And so these ideas come to him very natural. And that was really a great moment when I was sitting with him in the office and he came with that very simple idea, which was amazingly solving our problems of running just that, to give you an impression, a 10-fold cross-validation on a 2-dimensional grid would probably have taken about a week on a regular computer. And instead of that, I could run it in one evening, kind of. And so this was amazingly simplifying our situation on that application, actually. And that is also why I was very happy to there's 2 papers actually, except for the one where maybe now there is more, but that is actually 2 papers where this very simple technique was first mentioned. You see in one of them, Trevor was also involved. And so I was glad that I could use it to cite it when I was submitting the paper, to show also the referees that that is kind of a well-known technique. But yeah, so if you at any time plan to use it, there is references that you can take. So it's not new now. So now you can convince the referees that you are allowed to do it.
Okay, any other questions? No, I think that's all.
Perfect.